Understanding normal distribution in statistics. Normal distribution is a foundational concept in statistics, crucial for understanding how data behaves. The bell curve visually represents this distribution, showing how values cluster around the mean. This slide sets the stage for exploring key concepts and applications, emphasizing the importance of normal distribution in various fields. The decorative elements enhance the visual appeal, making it easier to engage the audience as we delve deeper into the topic. Key concepts. Normal distribution is essential for understanding data spread across various values. The bell curve is not just a visual tool, it helps us interpret data in real-world contexts, such as test scores and physical measurements. By grasping these key concepts, we can better analyze and predict outcomes in diverse scenarios. This slide highlights the significance of normal distribution in both theoretical and practical applications. Understanding normal distribution. This slide elaborates on the fundamental characteristics of normal distribution, emphasizing its symmetrical nature around the mean. The properties of the normal curve, such as the equality of mean, median, and mode, are crucial for statistical analysis. Understanding these characteristics allows us to apply normal distribution effectively across various fields, including engineering and finance, where data-driven decisions are vital. Normal distribution. The probability density function. Here, we delve into the probability density function, PDF, of normal distribution, which is key to understanding how probabilities are assigned to different values. The equation for normal PDF is the function f of x equals 1 divided by sigma times the square root of 2 pi, multiplied by e raised to the power of negative, open parenthesis, x minus mu, close parenthesis squared, divided by 2 sigma squared, where f, x, is the value of the probability density function at point x. Mu represents the mean of the distribution, which is the center of the curve. Sigma is the standard deviation, which measures the spread of the distribution. The formula presented illustrates the relationship between the mean and standard deviation, essential for interpreting the spread of data. The accompanying bell-shaped graph visually reinforces how areas under the curve correspond to probabilities, enhancing comprehension of this concept. Normal distribution. Mean, median, and mode of the normal distribution. This slide focuses on the central tendency in normal distribution, where the mean, median, and mode converge at the center of the curve. This property simplifies data analysis, making it easier to interpret results. The graph visually represents this concept, allowing the audience to see how these measures of central tendency relate to the overall distribution, reinforcing the importance of In this slide, we're discussing the determination of the mean of the normal distribution using the equation for the mean of a continuous probability distribution. The mean, denoted as mu, represents the expected value of a random variable in a continuous probability distribution. It is calculated using the integral mu equal integral minus infinity to plus infinity x into f, x, dx. This formula involves integrating the product of the variable, x, and its probability density function, f, x. The equation for the probability density function is inserted into the integral. On integrating and applying the limits, we get the mean of normal distribution as mu. In this slide, we're discussing the determination of the variance of the normal distribution using the equation for the variance of a continuous probability distribution. The variance, denoted as sigma squared, represents the variance of a random variable in a continuous probability distribution. It is calculated using the integral mu equal integral minus infinity to plus infinity, x minus mu, squared into f, x, dx. This formula involves integrating the product of x minus mu, squared and its probability density function, f, x. The equation for the probability density function is inserted into the integral. On integrating and applying the limits, we get the variance of the normal distribution as sigma squared. The standard deviation of the distribution is sigma. Here, we examine both the probability density function, PDF, and the cumulative distribution function, CDF, of the normal distribution. The PDF indicates the likelihood of specific values, while the CDF shows the probability of values being less than or equal to a given point. The graphs visually illustrate these concepts, helping the audience understand how they relate to one another and their significance in statistical analysis. This slide illustrates how changing the mean of a normal distribution affects its position along the x-axis. As we shift the mean, the entire curve moves left or right, but its shape remains unchanged. The graph effectively demonstrates this concept with multiple distributions, allowing the audience to visualize the impact of varying the mean on data interpretation. In this slide, we explore the effect of standard deviation on the normal distribution. A smaller standard deviation results in a steeper curve, indicating less variability, while a larger standard deviation produces a flatter curve, suggesting greater variability. The accompanying graph visually represents these changes, making it easier for the audience to understand how standard deviation influences data spread. This slide presents a histogram overlaid with a normal distribution curve, a powerful tool for assessing normality in data. The histogram displays the frequency of data points, while the normal fit curve helps visualize how closely the data approximates a normal distribution. This visual representation is crucial for understanding the distribution of data and identifying potential deviations from normality. Here, we introduce the QQ plot, a graphical method for testing normality. By comparing the quantiles of the data against those of a standard normal distribution, we can assess how well the data fits a normal distribution. If the points align along the 45-degree line, it indicates normality, making this tool essential for statistical analysis. This slide explains the normalized test statistic, which allows us to express data in standardized units. The formula provided illustrates how to convert raw scores into z-scores, facilitating comparisons across different datasets. The graph highlights the standard normal distribution, reinforcing the concept of standardization in statistical analysis. In this slide, we focus on how to read values from a normal probability table. By locating the z-score, we can determine the cumulative probability, which indicates the likelihood of a variable being less than or equal to that score. This practical skill is essential for applying normal distribution concepts in real-world scenarios. This slide continues the discussion on reading normal probability values from a table, providing specific examples of z-scores and their corresponding probabilities. The instructional text guides the audience on how to effectively use these tables, reinforcing the importance of understanding cumulative probabilities in statistical analysis. Here, we utilize the symmetry of the normal distribution to find probabilities. By examining the relationship between z-scores, we can determine that the probabilities for p, z plus 2.13, are equal. This symmetry is a fundamental property of the normal distribution, making it easier to interpret and analyze data. This slide presents a numerical example involving the heights of adult men, illustrating how to apply normal distribution concepts in practice. By calculating the probability of a randomly selected man being taller than 74 inches, we can demonstrate the practical implications of statistical analysis in real-world scenarios. Numerical example 1. Suppose the heights of adult men in a city are normally distributed with a mean height of 70 inches and a standard deviation of 3 inches. We want to find the probability that a randomly selected man is taller than 74 inches. Problem statement: the heights of adult men in a city are normally distributed with mean, mu, 70 inches, standard deviation, sigma, 3 inches, x, 74 inches. In this slide, we outline the steps to calculate the probability of a person being taller than 74 inches using the z-score. By breaking down the process into clear steps, we make it easier for the audience to follow along and understand how to apply these concepts in practical situations. Step 1. Finding the z-score. To find the z-score, we use the formula z equals the value of x minus the mean, mu, divided by the standard deviation, sigma. Inserting the values in the above equation, we get z approximately equal to 1.33. Step 2. Finding the probability. Next, we calculate the probability of being taller than a certain height. This is expressed as p of x greater than 74 equals 1 minus p of x less than or equal to 74. Using the z-table, looking up the z-score in a z-table, we find the probability of z being less than or equal to 1.33 is approximately 0.9082. Step 3. Calculating the desired probability. Finally, we determine the probability of being taller than 74 inches as p of x greater than 74 equals 1 minus 0.9082, which gives us approximately 0.0918. The shaded area in the graph shows the applicable probability in this case. This slide provides another numerical example, this time focusing on the weight of cereal packets. By calculating the z-score and using the z-table, we can determine the percentage of packets weighing less than a specific amount. This example reinforces the application of normal distribution in everyday contexts. The solution to this problem is similar to the earlier problem. In this slide, the solution for the numerical example 3 is discussed. A large number of tests of the line voltage to home residences show a mean of 118.5 volts and a population standard deviation of 1.2 volts. Determine the percentage of data between 116 and 120 volts. To find the z-scores, use the equation z equals x minus mu divided by sigma. Calculating z-scores. Z1 for 116 volts, 116 minus 118.5, divided by 1.2 equals minus 2.08. Z2 for 120 volts, 120 minus 118.5, divided by 1.2 equals 1.25. Using probability values for these z-scores, p equals p, z2, minus p, z2, equals 0.8944 minus 0.0188 equals 0.8756 or 87.56%. Approximately 87.56% of the data falls within this voltage range. This means most home voltage readings will be within 116 volts to 120 volts, demonstrating the predictable nature of normal distribution. Numerical example 4. It is desired to have 12.1% of the line voltage below 115 volts. How should the mean voltage be adjusted? Please refer example 3. The solution to this type of problem is the reverse of the previous problems. P, z, equals 0.121, 12.1%. Z equals minus 1.17. Z equals x minus mu, divided by sigma equals 115 mu, divided by 1.2 equals minus 1.17. Rearranging for mean, mu equals 115 plus 1.2 times 1.17 equals 116.4 volts. In order to have 12.1% of the line voltage below 115 volts, the mean has to be maintained at 116 volts.